Today, we are going to talk about a topic that every EV owner, or anyone considering buying an EV, absolutely cares about: power consumption and range. We often look at EV spec sheets, 0 to 100 kilometers per hour acceleration time, horsepower, and battery capacity. But you might have experienced this, or heard a friend complain: why does this same car have incredibly good energy efficiency in stop-and-go city traffic, but once it gets on the highway, the battery drains incredibly fast? Or conversely, some cars perform well at highway cruising speeds, but lack that aggressive push back in your seat feeling when starting off. Many people think this is just a matter of wind resistance, or simply because the car is heavy. But actually, the mastermind behind all of this is the motor at the heart of your EV. In the industrial sector, we often hear two terms: servo motor and variable frequency motor. If we apply this concept to electric vehicles, it becomes the ultimate showdown between the permanent magnet synchronous motors and the AC induction motor. These two types of motors, because their physical mechanisms for generating torque are completely different, directly lead to huge differences in their power consumption performance. Today, we are going to tear down these two motors and start from the foundational principles of electromagnetism to thoroughly decode for you why the difference in torque determines whether your car is truly energy efficient. First, we need to precisely translate industrial terminology into the language of electric vehicles. In the automation industry, the term servo emphasizes extremely precise control of position, speed, and torque. You tell it to turn a certain number of degrees, and it does so with micron-level errors. In the field of electric vehicles, what can achieve this servo-level precise control and possesses extremely high response speed is usually the Permanent Magnet Synchronous Motor. Permanent Magnet Synchronous Motor, abbreviated as PMSM. You can think of it as a naturally powerful, muscular strong man. Its rotor, which is the rotating part inside the motor, has super strong rare earth neodymium magnets directly embedded in it. On the other hand, what the industry often calls variable frequency is actually a driving method. But when we compare it with a servo, it usually refers to an inverter-driven AC Induction Motor. AC Induction Motor, abbreviated as ACIM. The design of this motor is quite fascinating. Its rotor does not contain a single magnet. The structure of its rotor looks just like a hamster wheel, which is why in engineering it's also called a squirrel cage rotor. It is cast from copper or aluminum bars. Okay, now we have two competitors. One is the motor with built-in magnets, the Permanent Magnet Synchronous Motor. The other one is the motor with just a metal cage inside, the AC Induction Motor. An EV's battery outputs direct current DC after being converted into alternating current AC by the inverter. It is sent into these two motors. Next, it's time to witness the magic and also witness the difference in power consumption. How does a motor make a car move forward? It relies on torque. But the way these two brothers generate torque, this is like stories from two completely different worlds. Let's first look at the Permanent Magnet Synchronous Motor. We all played with magnets as kids, like poles repel, opposite poles attract. The stator of the Permanent Magnet Motor, the stationary outer coils, when energized with three-phase AC power, will generate a rotating magnetic field. You can imagine the stator becoming a ring of electromagnets rotating clockwise. At this time, because the rotor itself is a super strong magnet, as soon as it senses the outer magnetic field rotating, it is immediately locked on tightly and rotates along with the outer magnetic field. However fast the outside rotates, it rotates just as fast. The two are perfectly synchronized. This way of generating torque is very direct and very aggressive. As long as the stator is energized, it can instantly generate a powerful electromagnetic attraction. This is why an EV is equipped with a permanent magnet motor. At 0 RPM, which is the exact moment you start from a standstill, can instantly unleash 100% of its maximum torque. The moment you step on the accelerator, the current command is converted into mechanical torque in mere milliseconds. This is the source of that servo-level push dash back dash and dash your dash seat feeling. What about the AC induction motor? It has a much harder time. As mentioned earlier, its rotor only has copper bars, no magnets. When the stator generates a rotating magnetic field, the copper bars inside are like standing still, watching the magnetic field sweep over them. According to Faraday's law of electromagnetic induction, when a magnetic field cuts through a conductor, the conductor will generate an induced current. So the copper bars in the squirrel cage are swept by the magnetic field, generating a current. Then, according to Lenz's law, this current-carrying copper bar in the magnetic field will experience a force, the Lorentz force. This force will push the rotor to rotate along with the rotating magnetic field. Listen carefully, there is a core. The most crucial physical phenomenon here, the reason the rotor turns, is because it generates an induced current when cut by the magnetic field. If today the rotor's speed is exactly the same as the outer rotating magnetic field, then to the rotor, the magnetic field is relatively stationary. There would be no cutting and no induced current. The torque would instantly become zero. Therefore, for an induction motor to generate torque, the rotor's speed must always, absolutely be slightly slower than the magnetic field's speed. In engineering, we call this slip. Let's use an analogy. A permanent magnet motor is like two magnets stuck together, running hand in hand, while an induction motor is like the stator holding a carrot, the rotating magnetic field, in front to lure the rotor, the rabbit to run. The rabbit chases desperately to eat the carrot, but can never catch it. This speed difference is the source of generating torque. Because of this passive induction characteristic, the initial torque burst of an induction motor, when starting, is usually slightly delayed. It's not as aggressive and directed as a permanent magnet motor. Having understood how torque is generated, we are finally getting to the core topic. Why the way torque is generated leads to differences in power consumption. This needs to be analyzed into extreme driving scenarios. First is low-speed, stop-and-go city driving. Second is long-distance highway cruising. Let's talk about the city first. Driving in the city. The things we do most often are braking for red lights, accelerating at green lights, and creeping slowly in traffic jams. In this state, the car frequently needs to output high torque to overcome its weight to start moving. But the RPM is usually very low. In this battlefield of low speed and high torque demand, the Permanent Magnet Synchronous Motor is the absolute king. It is incredibly energy efficient. Why? Because its rotor comes with built-in magnets. When you need torque, every bit of electrical energy sent in by the inverter can be 100% used to generate thrust with the rotor's magnets, turning into forward driving force. At low speeds, the energy conversion efficiency of a permanent magnet motor can even reach 95% to 97%. The electricity you paid to charge is barely wasted. It almost all turns into the force pushing the wheels. This is why many Japanese EVs, or models focused on city commuting, exclusively use permanent magnet motors. But what if we switch to an AC induction motor? The situation becomes tragic. At the exact moment of starting, the rotor of an induction motor has no magnetism. The electricity sent by the inverter cannot be entirely converted into forward driving force. It must first use a portion of the current, which we call excitation current, to forcibly excite the rotor's copper bars to generate a magnetic field. You can imagine this is like hiring workers to do a job. The permanent magnet motor worker brings his own tools and starts working immediately, while the induction motor worker comes empty-handed. And you have to spend money first to buy tools for him before he can start working. Inside a motor, when current flows through a conductor, it generates heat. This is called copper loss in engineering, which is $I2 or dollar loss. Because an induction motor constantly needs a massive excitation current to maintain the rotor's magnetic field, especially when starting at low speeds and needing high torque, this current will be very large. A massive amount of electrical energy simply turns into heat and is wasted. This results in the induction motor, during stop-and-go city driving, having significantly higher power consumption than a permanent magnet motor. Okay, hearing this, you might think, well, the induction motor is just garbage then. It consumes more power and isn't aggressive enough at launch. Why even use it? Don't rush. The most interesting part of engineering is that there is no absolute perfection, only trade-offs under different conditions. When the car gets on the highway, reaching speeds of 110 kilometers per hour or even higher, entering a long-distance cruising state, the whole battle undergoes a massive 180-degree reversal. During high-speed cruising, the torque required by the car is actually very small because it only needs to overcome wind resistance and tire rolling resistance to maintain speed. But at this time, the motor's RPM is very, very high. In this high RPM realm, the permanent magnet synchronous motor faces its fatal weakness. Remember that super strong magnet inside it? At low speeds in the city, it's a magic tool that helps you save power. But at high speeds, it becomes a huge burden. According to Lenz's law taught in middle school physics, when a magnet rotates at high speed inside a coil, it will act like a generator, producing a reverse voltage. This is called back EMF, electromotive force. The faster the motor spins, the larger this back EMF becomes. When the car speed reaches a certain level, the reverse voltage can become so large that it even exceeds the battery's own voltage. At this point, the battery's current simply cannot be pushed into the motor, and the car can no longer continue to accelerate. To solve this problem, engineers invented a technology called field weakening control. Simply put, the inverter must intentionally output a reverse current in FOC, vector control. This is called negative d-axis current, to forcibly cancel out the magnetic field of the rotor's magnets. Do you understand the terrifying part of this statement? At high speeds, not only can you not use all the electrical energy to push the car, you also have to intentionally waste a ton of electricity to fight against that magnet inside your own belly. This generates immense heat and energy loss. This is why many EVs equipped with a single permanent magnet motor, as soon as the speed exceeds 100 or 120 kilometers per hour, losing battery power as fast as an avalanche, their high-speed efficiency plummets. Furthermore, if you suddenly release the accelerator while driving at high speed, the permanent magnet motor's magnet is still rotating at high speed. It will generate powerful electromagnetic resistance passive kinetic energy recovery, which makes the car feel like it's being dragged. If you just want to use inertia to coast gently, the permanent magnet motor's magnet acts as a natural brake, eating up your kinetic energy for no reason. At this moment, let's welcome the strong return of the AC induction motor with a round of applause. Why can the induction motor achieve ultimate power savings during high-speed cruising? The reason is super simple. It can just play dead when you are cruising at a constant speed on the highway or coasting downhill and don't need to output any torque. The inverter can directly cut off the current sent to the induction motor. Instantly, the rotor's magnetic field disappears. The entire rotor becomes a completely non-magnetic, ordinary metal cylinder, spinning freely along with the wheels. Without magnets, there is no back EMF. Without backing EMF, there is no need to waste electricity on field weakening control. Without a magnetic field, there is no electromagnetic resistance. It can achieve true, zero resistance perfect coasting on the highway. This characteristic of being able to turn off the magnetic field at any time makes the induction motor's high-speed power consumption performance completely obliterate the permanent magnet motor. Let's summarize this paradoxical showdown between torque and power consumption. Permanent magnet motor servo level fears low-speed torque, extremely energy efficient for city starts, but is dragged down by its own magnets at high speeds, requiring power for field weakening, resulting in high coasting resistance. Induction motor variable frequency level, high power consumption at launch, needs extra current to create a magnetic field, but can cut off the magnetic field at high speeds for perfect zero resistance coasting, making it extremely energy efficient at high speeds. Since both have their pros and cons, if you were a car manufacturer's engineer, how would you design a perfect electric vehicle? Only kids make choices. As an adult, I want it all. This is the most mainstream and smartest solutions for today's top-tier dual-motor AWD EVs. Let's take Tesla, the brand everyone is most familiar with, as an example. Tesla's earliest Roadster and Model S because the founder admired Nikola Tesla, who invented alternating currents. Nikola Tesla exclusively used AC induction motors. This resulted in the Model S's excellent cruising performance on the highway, but it was at a disadvantage in stop-and-go city traffic. Later, when developing the Model 3, in pursuit of longer city ranges and a smaller size, Tesla fully pivoted to permanent magnet synchronous motors. But the most classic design appears in today's Model 3 and Model Y long-range dual-motor AWD versions. If you look at their chassis diagrams, you will find an extremely clever pairing. On its rear axle, they placed a permanent magnet synchronous motor, and on its front axle, they placed an AC induction motor. This is definitely not to clear out inventory. This is the crystallization of precisely calculated engineering. During low-speed city commutes and traffic jams, the car is entirely driven by the rear axle's permanent magnet motor. The front axle's induction motor is powered off at this time, in a dormant state of zero resistance free spinning. This guarantees ultimate city energy efficiency when cruising on the highway. If only a tiny amount of power is needed to maintain speed, it still relies on the rear wheel permanent magnet motor. But if you release the accelerator to coast, the front wheel induction motor still maintains zero resistance and won't cause any extra burden to the car. When you need to accelerate aggressively and floor the accelerator, or when the computer detects rear wheel slips, the system will, in mere milliseconds, instantly awaken the front axle's induction motor, sending in powerful currents to excite its magnetic field. And both front and rear motors will simultaneously unleash their maximum torque, bringing you a breathtaking push-back-in-your-seat feeling. This front induction, rear permanent magnet hybrid design perfectly combines the high efficiency of servo control with the flexibility of a variable frequency motor, achieving the ultimate balance between torque and power consumption. Of course, different car manufacturers have different strategies. For example, BYD, they have their own set of logic in battery technology and motor integration. Many of BYD's models, even dual-motor ones, also tend to use their own self-developed, high-efficiency, permanent magnet synchronous motors. To overcome the high-speed shortcomings of permanent magnet motors, BYD has put tremendous effort into the inverter's silicon carbide SiC modules, flat wire motor technology, and internal rotor cooling such as oil cooling, translated in context with above line. By pushing the extreme efficiency of the hardware, they compensate for the inherent weaknesses in physical characteristics. This is also a very hardcore engineering solution. Speaking of this, does everyone have a completely different understanding of the heart of an electric vehicle? Next time when you are looking at an EV spec sheet or going for a test drive at a showroom, don't just look at the 0 to 100 kilometers per hour acceleration time. You can ask the salesperson or do a little research yourself. Does this car use a permanent magnet synchronous motor or an AC induction motor or a hybrid of both? If it is a pure single front-wheel drive or pure single rear-wheel drive permanent magnet motor model, you'll have a good idea in your mind. This car is extremely suitable for navigating the urban jungle, and its city power consumption will definitely be excellent. But if you drive up and down the highway every weekend, you need to be mentally prepared that the power drop rate at high speeds might be faster than expected. Conversely, if you see a car particularly emphasizing that it uses an induction motor, then you can expect its cruising performance on the highway to be outstanding. Electric vehicle technology is still rapidly iterating. In the future, with the popularization of solid-state batteries and the maturation of 800-volt high-voltage architectures, motor designs will welcome even more incredible evolutions. Behind the technology, it is always the ultimate balance of physical laws and engineering trade-offs.